All right, so now we're going to analyze Newton's method as a fixed point iteration. Okay, so as we discussed before, if you're given a function f of x whose roots you seek, right, we consider an associated function g of x, which is equal to x minus f of x divided by f prime of x, right, whose fixed points are the roots of f of x. All right. Then, if you recall, it's like when we talk about the convergence properties of the fixed point iteration, right? I guess I should say that Newton's method is a fixed point iteration for this function g of x. Right, and so if you want to look at the convergence properties of Newton's methods, you can understand it in terms of the properties of this function g of x. And so in particular, we need to look at the derivative of g of x and find an interval around which the derivative of this is bounded from above in absolute value by 1. Okay, so you can take the derivative of g of x is equal to 1 minus, okay, so before I do that, let me write down g of x again. So g of x is equal to x minus f of x times f prime of x to the minus 1 power. So g prime of x is equal to 1 minus f prime of x, f prime of x to the minus 1. Right, so this is just a product rule, and then I have to differentiate this thing minus okay, so that's f of x, and then I have to differentiate the reciprocal, right? That's a minus 1. Then it's f prime of x to the minus 2, and then there's the derivative of f prime, so that's f double prime of x. Okay, so that is equal to, so this cancels this, right? And you're just left with f of x, f double prime of x divided by f prime of x squared. Okay, so let me make some observations about this. So the first of which is that g prime at the fixed point alpha is equal to 0. Okay, all right, and then right, and then you also need to observe that you need to pick alpha 0 so that the absolute value of the derivative of g is less than 1 in the interval sort of with delta, it's like about the fixed point alpha. Okay, so let me give you an example of using then this condition to figure out sort of an interval. It's like about a root for which Newton's method is guaranteed to converge. Okay. All right. So this is just g prime of x. let's look at an example. If you have f of x is cosine of x, you know that one of the roots is at pi over 2. So let's try to find some interval around pi over 2 for which the method is guaranteed to converge. Okay, so g prime of x via this calculation is equal to minus cosine of x over sine of x, the whole thing squared. Okay, and you can check that g prime of x is equal to 1, okay, when x is equal to pi over 4 and 3 pi over 4. So as long as alpha 0 is in the interval between pi over 4 and 3 pi over 4, right, as long as you start with this initial starting value, then the Newton method will converge to the root at pi over 2. Okay. So let me sort of just circle back and remind you again of why it is that we have this. So the main idea is that Newton's method is a fixed point iteration. Xn plus 1 or alpha n plus 1 is equal to g alpha n, and fixed point iterations converge if the absolute value of the derivative at g is bounded from above by 1 near x equals to the fixed point. Okay, so all right. So what basically happens is that you have quadratic convergence of Newton's method if the absolute value, if the derivative of f at alpha is not equal to 0. And that's because, if you recall, g prime of x was f of x, f double prime of x divided by f prime of x squared. All right. So we want this g prime to be less than 1, okay, and it will be 0 so long as f prime at alpha is not 0, because f at alpha is 0. Okay, so all right, and actually the fact that g prime at alpha is 0 means that it's converging faster than linearly, and so it's going to be superlinear convergence, but in particular it's going to be quadratic convergence in this case. Okay, and what happens is that if f prime at alpha is equal to 0, then the Newton method only converges linearly, and Newton method converges linearly. And so that's something which you'll be asked to show. It's like on one of the homework exercises. Okay. All right. So I can also say a little bit about the secant method and the method of false position with this. So, secant method and false position. Okay, so you can show that the limit as n tends to infinity of the error at the n plus first stage divided by of error at the nth stage raised to the power p is equal to m, where p is equal to 1/2 1 plus square root of 5, which is approximately 1.618. Okay, so you have what is called superlinear convergence, which is to say that it is faster than linear but slower than quadratic. Okay, so I should also remark that so secant and the method of false position are very similar. And the secant method usually converges a bit faster. In the sense that this constant m is smaller. But false position is guaranteed to converge, whereas secant is not necessarily guaranteed to converge. Okay. So there is sort of a trade-off, if you will, it's like between these two methods. All right, so that's basically what I wanted to say for now for root finding for scalar valued functions. The next thing we'll be discussing is how do you go about solving linear systems of equations, and then we'll circle back to talk about root finding for vector valued functions in a little bit. But for now, it's like, let me just stop here.